I want you to imagine London. Um, the year is 1803,
Okay.
and we are standing in this gloomy, damp courtyard of Newgate Prison.
Oh, sounds inviting.
Right.
Hmm.
And we're looking at a public spectacle that is, well, it's equal parts gruesome and completely revolutionary.
I think I know where this is going.
You probably do. So the Italian physicist Giovanni Aldini has set up a demonstration, and he's using the fresh corpse of an executed murderer, this guy named George Forster.
Right, the famous Newgate experiment.
Exactly.
Yeah.
So Aldini connects this really primitive battery to the body, and he runs an electrical current right through it.
Wow.
And suddenly the corpse's jaw begins to quiver.
Ah.
The facial muscles contort into this horrible grimace. One eye actually pops open.
That is just...
And then the right hand clenches and literally punches the air. The legs start jerking violently.
I mean, it was pure terrifying theater. People in the audience, they genuinely thought the man was coming back to life.
Right.
Like some historical accounts say people actually fainted just watching it happen.
I would have fainted, honestly. But it cemented this terrifying and, I guess, fascinating idea into the public consciousness. In fact, this very idea is often cited as the direct inspiration for Mary Shelley's Frankenstein.
Oh, totally.
It proved in the most visceral way possible that electricity and life are inextricably linked.
Which is really the core of what we are unpacking today because, you don't need a massive primitive battery from 1803 to make your muscles move.
You have your own internal electricity.
Exactly, you have your own. And unlike a copper wire plugged into a wall, the biological version is incredibly dynamic.
So welcome to today's deep dive. Our mission today is to figure out exactly how the body's internal electricity actually works.
Yes, and we've got some great sources for this.
We really do. We are pulling from this fascinating stack of anatomy and physiology research, historical texts, and even some wild modern biophysics debates to understand what scientists call the action potential.
The action potential.
Right. It is the all-or-nothing electrical signal that serves as basically the basic unit of information transfer in your nervous system.
Go.
And I promise you we are absolutely avoiding dry textbook jargon today.
No textbooks agreed.
By the end of this conversation, you'll discover how everything from the deadly poison of a pufferfish to the delicate feeling of a feather brushing against your skin, it all comes down to a microscopic, beautifully choreographed electrical dance.
It really is a dance. And to truly understand how a nerve fires, how it sends that electrical signal from your brain all the way to your toe, we actually need to start by looking at what it is doing when it is seemingly doing nothing.
Right, doing nothing.
Because as you know, nothing in biology is a total illusion.
It's never doing nothing. To understand the spark, we have to understand the loaded spring.
That's a great way to put it. A neuron at rest is not an empty wire waiting for someone to flip a switch. It is a highly charged battery.
Oh.
In a typical neuron, the inside of the cell sits at a resting membrane potential of roughly negative 70 millivolts compared to the outside.
Negative 70 millivolts.
Right. And it achieves this negative charge by meticulously maintaining an unequal concentration of ions. Specifically, it hoards potassium inside the cell, and it keeps a vast surplus of sodium on the outside.
Okay, so reading the sources, they outline how much energy this actually takes.
Yeah.
And it really reframed things for me.
It's exhausting for the body.
Yeah. I always like to think of this using a battery and pump analogy. Maintaining that negative 70 millivolt charge is active, exhausting work. The cell is constantly fighting against the natural laws of the universe.
Right, because the universe always wants equilibrium.
Exactly. It wants all those sodium ions on the outside to just rush in and balance things out. But a cell at total equilibrium
Is a dead cell.
is a dead cell. So to stop that from happening, the neuron has this microscopic machine embedded in its wall called the sodium-potassium pump.
And this pump is just relentless. It was discovered by a Danish scientist named Jens Skou back in 1957, which eventually won him a Nobel Prize.
Oh, wow.
Yeah, and the sheer scale of the energy expenditure here is staggering. Your brain uses about 20% of your body's total energy, despite being just a tiny fraction of your body weight.
Just a few pounds.
Right. And a massive chunk of those calories you consume every day is dedicated simply to powering these tiny pumps.
Just to maintain that resting baseline.
Man.
That is wild. And the pump has a very strict exchange rate too, right?
It does.
To keep the battery charged, it burns one molecule of ATP, which is the body's fundamental energy currency,
Okay.
to grab 3 sodium ions that have leaked into the cell, physically push them outside, and then pull 2 potassium ions back in. 3 out, 2 in.
3 out, 2 in,
Right.
constantly. But we should clear up a really common misconception here, though.
Okay, what's that?
Well, because it uses so much energy, people often assume the pump is what actively causes the nerve to fire an action potential.
Oh, right, like it's doing the
Right?
firing.
Exactly,
But-
but it doesn't.
It's just the maintenance crew sweeping up in the background.
Precisely. It operates on a much, much slower timescale. The movement of ions during a single electrical spike is a vanishingly small fraction of the total ions in and around the cell.
Yeah.
The overall concentrations, they barely budge. A neuron could fire thousands of individual action potentials before the pump even needs to catch up to restore the deficit.
That's crazy. Okay, so the battery's fully charged, the spring is loaded, the inside of the cell is sitting at negative 70 millivolts, desperate for sodium to rush in. What actually happens when someone pulls the trigger?
Well, the trigger is what we call a stimulus.
Right.
And this could be photons of light hitting the back of your retina, a chemical binding to a receptor, or a neighboring neuron sending a signal across a synapse.
Any kind of input.
Exactly. That stimulus starts to depolarize the cell, meaning it makes that resting negative 70 millivolt charge slightly more positive.
Okay.
If the stimulus is incredibly weak, the voltage might bump up a little and just naturally decay. But if the stimulus is strong enough to push the voltage past a very specific threshold, usually around negative 55 millivolts,
Then the dam breaks.
an unstoppable chain reaction is triggered.
The action potential, the exact moment the neuron fires.
Exactly. At negative 55 millivolts, specialized proteins in the cell membrane called voltage-gated sodium channels suddenly snap open.
Okay.
And because there is an absolute ocean of sodium outside, and because the inside of the cell is negatively charged, those positive sodium ions aggressively flood into the cell.
Right. Opposite charges attract.
You got it. This massive influx of positive charge causes the internal voltage to swing all the way up past zero into positive territory, peaking around positive 40 millivolts.
Wow, so from negative 70 to positive 40.
Yep. It is a runaway positive feedback loop. Sodium rushes in, which triggers more channels to open, which lets more sodium in.
Yeah.
And the entire violent swing from negative to positive happens in about 1 to 2 milliseconds.
Okay, let's unpack this, because I'm stuck on something you just said.
Sure.
The sources refer to this as an all-or-nothing event. Below the threshold, nothing happens.
Yeah.
But the moment you hit negative 55 millivolts, you always get the exact same spike, swinging all the way up to positive 40 millivolts. The volume of the signal never changes.
That's right.
If that is true, how does my brain know someone is lightly tapping my shoulder versus like punching me in the arm? The math just doesn't make sense to me.
Oh, that is the perfect question to ask because it highlights a major gap in how we intuitively think about these signals.
Okay, good. I'm not crazy.
No, not at all. The intensity of a sensation, or a motor command for that matter, is not communicated by the size or the height of the electrical spike. Like you said, the amplitude is always identical.
Right.
Instead, the intensity is encoded by the frequency of the spikes. This is a concept called rate coding.
Oh, okay. So it's not about how loud the shout is, it's about how often they are shouting.
Exactly. A gentle tap on the shoulder might trigger 3 action potentials per second from a sensory neuron in your skin.
Right.
A hard punch might trigger 80 action potentials per second from that exact same neuron. And your brain interprets that rapid-fire machine gun frequency as a stronger, more intense physical stimulus.
You know, it is remarkably like a vintage telegraph machine.
Oh, that's a good comparison.
Yeah, like the dots and dashes are always the exact same volume on the receiver, but how fast the operator is frantically tapping the key tells you how urgent the message is.
That is a beautiful way to visualize it. But, we also have to consider the other side of the equation.
Right, turning it off.
Starting the signal is crucial, but stopping it is literally a matter of life and death. If those sodium channels just stayed open, the cell would short out and die. The action potential requires a built-in delayed break.
And I was reading the notes on this, and the mechanism for how the cell stops the signal is wild. It's an actual physical structure, almost like a literal plug.
It is structurally remarkable, yes. Within about a millisecond of the channel opening, a physical protein appendage on the inside of the sodium channel swings up. It is literally shaped like a ball attached to a molecular chain, and it physically plugs the pore of the channel from the inside.
So it just clogs it up.
It just clogs it up. The sodium influx abruptly stops, and simultaneously, a completely different set of doors, the voltage-gated potassium channels finally swing open. They're much slower to react to the initial voltage change than the sodium channels were.
So they're on a delay.
Yes.
And since there is a ton of potassium waiting inside the cell, and the inside is now positively charged at plus 40 millivolts, those positive potassium ions desperately want out.
Right.
They are repelled by the positive charge.
Exactly. They rush out of the cell, taking their positive charge with them, which abruptly drives the internal voltage back down into negative territory.
Back to the baseline.
Right. This phase is called repolarization. It actually overshoots the resting baseline for a brief moment, a phase called the hyperpolarization undershoot, before settling back down to the comfortable resting state of negative 70 millivolts, perfectly primed and ready to fire again.
Okay, so we have this highly precise millisecond by millisecond sequence. Sodium rushes in, then potassium rushes out.
That's the dance.
And that microscopic sequence is the fundamental machinery of how you feel pain, how you think about a memory, how you move your leg.
Every single action.
So what happens to the human body when something deliberately breaks that machinery?
Well, nature has engineered some incredibly potent ways to break it. If we look at the pufferfish, or the fugu, which is considered a really dangerous delicacy in Japan, it carries a neurotoxin called tetrodotoxin, or TTX.
TTX?
And by the way, the beautiful, tiny, blue-ringed octopus uses the exact same toxin.
Oh, I've seen videos of people holding those on the beach. It's terrifying.
Do not hold a blue-ringed octopus, because TTX is a molecule that just happens to be perfectly shaped to fit into the outer pore of those voltage-gated sodium channels we just talked about.
No.
It acts exactly like a cork hammered into a wine bottle.
Wow. So if the entire trigger for the action potential is that initial violent rush of sodium into the cell and the channels are corked from the outside, the dominoes never start falling.
Exactly. The neurons simply cannot fire. Victims of fugu poisoning experience a progressive ascending paralysis.
That sounds horrific.
It is. You might feel your lips and toes go numb first. Then you lose the ability to move your legs, then your arms. Eventually, it paralyzes the diaphragm and you stop breathing.
Wow.
But the truly terrifying part of TTX poisoning is that the victim often remains fully conscious throughout the entire ordeal.
Wait, really? How is it even possible to be awake and experiencing that if your entire nervous system is shutting down?
Because TTX doesn't cross the blood-brain barrier very effectively.
Oh.
Yeah, so the sensory and cognitive processing centers safely tucked inside the central nervous system, they continue to function perfectly, even as the peripheral nerves and the respiratory muscles out in the body go completely silent.
So you are entirely awake, but trapped in a body that cannot send a single electrical command.
Exactly. And there is no antidote either. You just have to be put on a mechanical ventilator to keep you breathing until the toxin naturally unbinds from the channels over hours or, days.
That is wow. But here's where it gets really interesting, because you listening to this have probably never eaten a pufferfish.
Yeah.
But you have almost certainly encountered a drug that does the exact same thing to your nerves, and you probably paid a doctor to give it to you.
Oh, definitely.
Think about lidocaine, or really any of the local anesthetics your dentist uses before they drill a cavity.
Yep.
They work on the exact same physiological principle. They physically plug the voltage-gated sodium channels to stop the nerve from firing.
With one very slight structural difference.
Right.
Anesthetics like lidocaine plug the channel from the inside of the cell rather than corking it from the outside like the pufferfish toxin.
Right. And the history behind that class of drugs is fascinating. It traces back to 1884, when an ophthalmologist named Carl Koller was desperately looking for a way to numb the eye for surgery.
Because eye surgery back then without anesthesia, yikes.
Yeah, horrible. So on a suggestion from his colleague, a guy you might have heard of, Sigmund Freud.
Freud, of course.
Yeah, Koller used cocaine. Cocaine was the first local anesthetic. And it works by chemically blocking those sodium channels from the inside, so the pain signal literally cannot start.
Incredible.
Now, we eventually synthesized much safer, non-addictive versions like lidocaine, but the fundamental mechanism stopping the sodium rush to stop the feeling of pain is identical.
It is. And if we connect this to the bigger picture of human health, it highlights a profound principle in biology. There are many ways to break a system, but they often result in the exact same functional failure.
Right.
For instance, multiple sclerosis, or MS, achieves a strikingly similar downstream effect.
The paralysis, the numbness.
Yes. The signal basically fails to get through, but MS does this through an entirely different structural mechanism. MS doesn't plug the ion channels. Instead, it is an autoimmune condition where the body's immune system attacks the myelin sheath.
Okay, let's lean into an analogy here, because visualizing the myelin makes all the difference. Earlier, we talked about the action potential being like a line of falling dominoes.
Right.
Well, in a normal nerve wire, you don't actually need a continuous line of dominoes packed tightly together. You have this fatty tissue called myelin acting as thick insulation wrapped around the nerve.
It's like the rubber coating on a wire.
Exactly. But it doesn't cover the entire wire, though. It leaves tiny, evenly spaced, exposed gaps along the wire.
And those gaps are called the nodes of Ranvier.
Right. So because of that fatty insulation, the electrical signal doesn't have to slowly knock over every single microscopic domino down the entire length of your leg. The insulation prevents the electrical charge from leaking out, so the signal can basically jump rapidly from one exposed gap to the next.
Yes, and biologists call this saltatory conduction, from the Latin word meaning to jump.
To jump, right.
It dramatically boosts the speed of the nerve impulse, taking it from a slow crawl to a lightning-fast transmission.
So if the nerve signal is a line of falling dominoes, myelin is what lets us space those dominoes far apart so the signal leaps forward. But if multiple sclerosis strips away that myelin, it's like someone removed the intermediate dominoes in the line.
That's a perfect way to picture it.
Right. The first domino falls. But because the insulation is gone, the electrical current just leaks out into the surrounding tissue. The charge dissipates, and by the time it reaches the next gap, it's too weak to knock over the next domino.
The action potential essentially fizzles out before it ever reaches the muscle. It is the exact same functional result as the dental anesthetic blocked conduction, but it is a structural, physical breakdown of the wire rather than a chemical plug in a channel.
Totally. And, thinking about all these microscopic structures, the ion channels, the molecular ball and chains, myelin gaps, it is so easy for us to sit here today and just take for granted that we know they exist.
Oh, absolutely.
But I was blown away reading the history of how scientists actually proved this. Like, how do you map out the molecular mechanics of an ion channel in the 1940s and 50s when you literally couldn't even see a molecule?
They were doing it totally blind.
Exactly. They had no electron microscopes capable of seeing a tiny protein embedded in a cell membrane.
No, it was an immense struggle. The breakthrough came primarily from scientists Alan Hodgkin, Andrew Huxley, and Bernhard Katz. They knew they couldn't see the tiny channels in a human nerve, so they solved the problem by finding a very, very large nerve.
The giant axon of the squid.
Yes, the giant squid.
Specifically, a species called loligo. This detail is just incredible to me. This particular nerve axon inside the squid is nearly 1 millimeter thick.
Which is massive for a cell.
Right. Now, 1 millimeter doesn't sound huge to us, but for a single biological cell, it is an absolute monster. It evolved to be that large because the squid needs to send a lightning-fast signal to its muscles for a rapid escape response. But for Hodgkin and Huxley, it was a practical miracle. It was literally big enough that they could physically thread a delicate silver wire straight down the inside of the living cell to measure the internal voltage.
It was a painstaking feat of experimental biology.
Seriously.
Around 1949, they began manipulating the physical environment around this squid axon. They had to overcome the prevailing theory of the time, which was proposed way back in 1902 by Julius Bernstein.
Right, the 1902 theory.
Yeah, Bernstein believed that an action potential was simply the cell membrane temporarily breaking down, allowing the internal voltage to collapse to zero and nothing more.
Just to collapse to zero. But because Hodgkin and Huxley had that silver wire physically inside the squid nerve, they proved the old theory completely wrong.
Exactly. By varying the amount of sodium in the seawater surrounding the squid nerve, they proved that the electrical spike didn't just stop at zero. As we discussed earlier, it violently shot past zero, overshooting into positive territory.
Into that plus 40 millivolt range.
Yeah, right. And, crucially, they proved that the height of that overshoot was entirely dependent on the specific concentration of sodium outside the cell.
So they figured out it was a sequential, ion-specific event. Sodium in, then potassium out.
Yep.
But they didn't stop at just measuring it. They took it to a level of abstraction that is hard to wrap your head around.
Oh, the math!
Yes. In 1952, Hodgkin and Huxley published a series of papers culminating in a purely mathematical model. It was a set of complex differential equations that perfectly predicted exactly how and when the nerve would fire.
And to make the math work, they had to infer that there must be independent voltage-sensitive gates for sodium and potassium hiding in the membrane.
So they predicted a physical door they couldn't even see.
Completely blind, yeah. They just completely trusted their math.
That is just brilliant. It took decades of technological advancement, new techniques to clamp individual cells by Erwin Neer and Bert Sackman in 1976, and eventually bouncing X-rays off proteins by Roderick McKinnon in 1998 to finally get a physical picture of an ion channel.
Decades later.
And when they finally saw the physical machinery, it operated exactly the way Hodgkin and Huxley's 1952 math said it would.
It really remains one of the great triumphs of 20th century science.
Yeah.
But as much as we have figured out, this feels like the perfect moment to dismantle a lingering misconception. Because even with Nobel-winning math and X-ray proof, people still tend to visualize the actual movement of the signal wrong.
Okay, yeah.
The biggest trap is thinking about the action potential, like electricity flowing through a copper wire in your wall.
Right, because in a copper wire, electrons are literally traveling from one end of the cord to the other at a massive fraction of the speed of light.
Yes.
But in your nerves, no individual ions are actually traveling down the length of your arm. Like a single sodium ion doesn't enter the nerve in your spinal cord and travel all the way down to your fingertip.
Exactly. The local depolarization triggers the adjacent patch of membrane to open its own sodium channels. The wave of voltage change is what propagates forward, not the ions themselves. Your domino analogy earlier captures this perfectly. When you push the first domino, that physical block of wood doesn't slide across the floor to the end of the line. It just knocks over the one immediately next to it.
Ah, I love that. And that distinction, brings us to a really fascinating edge of modern science. Because even when a topic seems entirely settled, when it has been textbook science for 70 years, there are always unresolved mysteries.
Definitely.
I saw this debate in the sources, and I really need you to translate it for me. What is the soliton theory?
This raises an important question. So it is a fascinating, albeit minority, debate pushed by a pair of biophysicists named Thomas Heimberg and Andrew Jackson in the 2000s.
Okay.
They pointed out an anomaly in the textbook model. When a real nerve fires an action potential, it doesn't just change electrically. The nerve actually undergoes a measurable physical change.
Physical change, like what?
It briefly alters its thickness, its temperature, and its mechanical tension during a spike. The purely electrical Hodgkin-Huxley model doesn't predict that physical swelling, and it honestly doesn't need it for the math to work.
So they are arguing that the action potential might not fundamentally be an electrical event at all.
Exactly. They suggest the action potential might actually be a mechanical thermodynamic density wave, a physical ripple, or a soliton traveling through the fatty lipid membrane of the cell.
Okay, unpack mechanical density wave for me. What does that actually look like?
Think of a sound wave traveling through water, or the way a bullwhip creates a physical ripple that travels down the leather when you snap it.
Oh, okay.
They are arguing that the nerve signal is essentially a physical acoustic shock wave traveling down the fat of the cell. In their view, the opening of the ion channels and the electrical currents we measure might just be a side effect of this physical shock wave squeezing the membrane as it passes by.
That is wild to look at decades of Nobel Prizes and say, yes, the ions move, but the electricity is just the exhaust, not the engine.
Basically, yes.
Now, we should be clear for anyone listening, this is very much a fringe position in the scientific community right now.
Oh, completely. The predictive power of the classical ionic model is overwhelming. But it is such a great reminder that science is never a closed book.
We must always be willing to look at the anomalies and question our foundational assumptions.
Absolutely.
Well, let's pull all of this together and look at the journey we've taken today. We've seen that the action, potential, the fundamental spark of your nervous system is an all-or-nothing domino effect.
Right.
It relies on a meticulously timed dance.
Yeah.
Sodium rushing into the cell, followed immediately by potassium rushing out.
The 1-2 millisecond dance.
Exactly. We learned that the nerve's resting battery is actively, exhaustingly maintained by the tireless work of the sodium-potassium pump. And we discovered that this single microscopic mechanism is the bottleneck for everything from the local anesthetics at your dentist's office to the devastating effects of a disease like MS.
It truly is the biological foundation of human experience. And as we wrap up, I want to leave you with one final thought to mull over. It connects this 70-year-old biology to the absolute cutting edge of neuroscience today. The sources detail a modern technique called optogenetics.
Oncogenetics, yes.
Scientists have figured out how to take light-sensitive proteins, which are essentially modified ion channels, and insert them into specific neurons in a living brain.
Which means they can control those individual neurons with lasers.
By simply shining a specific wavelength of light into the brain, researchers can force those modified sodium channels to snap open. They bypass the normal stimulus entirely and trigger an action potential on demand.
Wow.
And by doing this in a lab, scientists can now literally control a subject's movement, alter their behaviors, and even artificially activate or rewrite specific memories just by turning a light switch on and off.
Which brings us all the way back to Aldini and the corpse in the courtyard in 1803. The sheer shock that manipulating electricity dictates life.
It asks a much deeper philosophical question now, though. If manipulating a few microscopic sodium channels with a flash of light can literally change a memory or alter a core behavior,
Right.
it's going to invite you to consider, is everything that makes your consciousness, your personality, your deepest, most profound feelings, is it all ultimately just a fleeting sequence of ions washing back and forth across a microscopic barrier?